So in this video, we're going to look at the question C of the section 2 2023. So let's see. It says the electrical power from the wind farm is transferred to the shore using high voltage direct current. So at 320 kilo volts with respect to Earth. And the cable is used to transfer the power, typically consists of a 2.2 centimeter radius copper core surrounded by a cross-linked polyethylene insulation of radius 4 centimeter, which itself is surrounded by a protective metal system. The greatest length in a North Sea project will be 265 kilometers, and it gave us the resistivity of the copper and the XLPE, which I think is the second layer of insulation. Yeah, that's the insulation layer. And so the first part of the question wants us to calculate the resistance of the copper wire, copper core, and the power dissipated as heat, and the percentage loss in the copper if the cable transfers 800 megawatts of power. So let's see, part 1. And first of all, calculate the resistance of a copper core. So the resistivity is given as 1.68 times 10 to the minus 8, and then the length is given, and also the area. Yeah. So let's see. The resistance will be equal to the resistivity times L over A, and which is equal to, in this case, that will be 1.68 times 10 to the minus 8, and times the length, 265, I believe, and then times 10 to the 3 over the area. The area is, it said, consists of a 2.2 centimeter radius. So that will be 0.022 squared pi for the area, and that will be equal to let's see, 1.68 minus 8 times this is 265 over 0.022 squared pi is over here, and that is 2.992, like 2.928 ohms. And also wants to calculate the percentage loss in the copper. So also the power dissipated as heat. So the power dissipated as heat. So in order to calculate the power dissipated, P is equal to VI, the voltage, times the current. Now in this case, I think we can use this equation to simplify it. So I squared times R. And how do we calculate the current? The current in this case, so the power dissipated as heat. So yeah, I think we should calculate the current first. So using the same equation, P is equal to VI, we can calculate the current is equal to, that's 800 megawatts, so that's 10 to the 6 over the voltage, which is given as over here, so that's 320 kilovolts. Yeah, 320. 320 kilovolts, and that leaves us so that's 1 over 4. yeah, and then times 10 to the 3, wait, no, 10 over 4, yeah, 10 over 4, and that will be equal to, that's 2.5, so 2500 amperes, and so therefore the power dissipated with, that seems a bit high. Let's see. So the power dissipated will be equal to I squared times R, which is calculated earlier. So I squared, that's 2 squared times 2.928. And yeah, that's okay, so that's 18.3, this is megawatts. And then the question wants to calculate the percentage loss. So the percentage loss would then be, let's see, L for loss percentage is equal to 18.3 over 800. Now that will be so wait, 18.3 over 800, so that's around 2.3 percent loss, and these will be the three answers to the question. Over here, here, and here. And then part 2 says calculate the resistance of XLP insulation between the copper core and the metal screen, and hence calculate the leakage current, power, and percentage loss due to the leakage current when operating at 320 kilovolts. So the XLP layer is the insulation layer, so that's this layer over here, and so basically it's between the copper and the metal screen, and the information gives us it has a radius of 4 centimeters, and yeah, I think, and also the resistivity. So how do we calculate the resistance in this case? It's not like a wire, or you can say a cylindrical shape. It's like a ring-shaped setup. So the resistance is defined as rho L over A. Now in this case, the area. I think we should take it as the area in contact with the XLP insulation. So okay, so first of all, the resistivity is given as 1.94, 1.97, 1.97, and then times 10 to the 14, and then you time it by the length. I suppose that's just the difference between the radius given, so that would be 1.8 centimeters. 1.8, so that's 0.018 meters over the area, so I suppose that is 2.2, and then times 2, so that's 4.4 centimeters, that's diameter, so 4.4 pi, and then times the length, so 0.044 pi, and then you time it by the length of the the cable, so that's 265. 265 times 10 to the 3. And yeah. So then it will be 1.97, 14, and then times 0.018 over 0.044 pi. And then times 265 and then 10 to the 3. So that is a rather large number. Wait, let's see. Just checking if there's anything. The length, yeah. Okay, I don't think there's anything incorrect over here. So that's 96 mega ohms, 96.8. Let's go with this first. And then we want to calculate the leakage current. So the leakage current would be I is equal to V over R. Therefore, so the voltage will be it's given as 320 kilovolts, and then over this, so that's 6, and then leakage current will be equal to, so that's 320, that's 10 to the 3 over, yeah, so which is 0.003 say 33 amperes. And then the power would be simply I squared R, which is equal to, let's see, 0.0033 squared times this, that is 1045, let's say just take all the decimal places, watts. And then the percentage loss due to the leakage current, so that will be over the total power. So it's given the previous question, that is 800 megawatts. Yeah. So this will be a rather small percentage, so that's over divided by 826. So that is around like 0.00013%. And that will be answer to the question. So that's this part, and then the current as well, the power, and the percentage loss. And then let's see part 3. So part 3 says the thermal conductivity of XLPE is equal to 0.28 watts meters per Kelvin. Okay, thermal conductivity. And so when the temperature drop across all thermal barriers except X, PLE is negligible. So calculate the operating temperature of the copper core at 800 megawatts given the ambient C temperature is 7 degrees Celsius. Okay, so the temperature reaches an equilibrium when the heat when the heat generated is equal to the heat dissipated. So, oh well, actually the rate at which the heat is generated is equal to the rate at which the energy is dissipated. And in this case, that will be simply the power. The heat at which it is generated will be simply the power. Yeah, okay, so the power in this case will be the voltage times current, and it's also given, which is 800 megawatts. And the temperature reaches an equilibrium when this is equal to the the rate at which heat is conducted in this case. So that will be K for thermal conductivity, and then I think you time it by the area, and then also the change, the difference in temperature over the length. And so 800 times 10 to the 6 is equal to the thermal conductivity is 0 0.28, 0 0.28, and times the area. The area, I suppose the same. That is, I think I calculated earlier. Yeah, it's just 0.044 pi, and then you time it by the length. And then the difference in temperature. So I'm just going to leave it with delta T, so yeah. And then do the calculation later. So, and then divide by the length. The length in this case, they didn't give us the length of any of the other layers. I mean the radius. So we can assume that the length is just the width of the insulation layer, XLP. Yeah, okay, so that will be 4 centimeters minus 2.2, which is 1.8 centimeters, and that is 0.018. Yeah, and then we can calculate delta T. So delta T will be equal to, I'm just going to put it in, so 800 and then 10 to the 6 times 0.018 over 0.28, and then time it by 0.044 pi, and then time it by 265, yeah, 265, and then yeah, I think that's it, and that gives us 1404, let's say 1404, yeah, and then so therefore the temperature at which the copper core is operating will be 7 degrees Celsius plus this, which is 1411 degrees Celsius. And yeah, and that will be the answer to the question.